Hi, so for today we are going to talk about U-substitution in integral calculus. And this is a basic topic in integral calculus and a technique that is really commonly used, no, in all parts of integral calculus as you go study the calculus. Okay, so we're going to solve some problems here involving U-substitution and hopefully this will be a helpful video for you. Okay, so for number one, why do we need to use U-substitution? Okay, so U-substitution is another technique by which we can solve integrals, because in a given different integrals, we have different approach on how we are going to solve a specific kind of integral. So one of which is the U-substitution. So take a look at this example. We have to get the integral of 2x plus 5 multiplied by x squared plus 5x raised to 7 dx. So in the first encounter of this problem, you would see that this might seem a hard problem because of the raised to 7. So the question that comes to your mind, am I going to expand this product or not? Okay, but if we are going to if you are going to look at it carefully, we have here a first term of 2x plus 5, and we have here an x squared plus 5x raised to 7. So the technique that the U-substitution is telling us is that if we find a term inside or in the integrand that will serve as a u, and if we get that u and differentiate that u, we will find another term in the integrand containing the same derivative, then we can let U-substitution, okay, applied into that integral. So for example, so as you can see here, if you are going to observe carefully, we have x squared plus 5x, okay, which happens if I get the derivative. Let's say if I get the derivative of x squared plus 5x, okay, that would be 2x plus 5, which happens to be this one. Okay, so in this way we can use the technique U-substitution. So on the other hand around, if I'm going to differentiate 2x plus 5, I know that that would be 2 only, and there are no 2's inside the integrand. Okay, the two constants. So in employing U-substitution here, I'm going to let u x squared plus 5x, and then we're going to get the derivative of u on the left side, which is du, okay, and differentiate x squared plus 5x with respect to x on the right side. So that becomes 2x plus 5 dx. And if we're going to carefully look at this equation, so we have x squared plus 5x, we can rewrite it as this. Then we have 2x plus 5, okay, dx. Okay, so what we are seeing right now is that this 2x plus 5 dx is simply du. So that's why it's called U-substitution, is because we are going to temporarily change the variable x into u, or any other variable rather than x given in the integral. So what are we going to do? We are just going to simply substitute x squared 5 plus 5x. We let that as our u. So this becomes u raised to 7, okay, because of the we let that as our u. And then this 2x plus 5 dx, okay, as we can see, we have dx here, I'm sorry. This 2x plus 5 dx, we have dx here because we differentiate with respect to x. So we have 2x plus 5 dx here. So, and that is equivalent to du. So imagine if you're going to substitute it as U-substitution, okay, what we are seeing right now is an integral of u raised to 7 du. So we have changed the variable x into u. For what? For what reason? For us to integrate it easily. So we can see that if we integrate this, this becomes a power rule, u raised to 8 all over 8 plus c. Okay? So if once we are done integrating, we must go back to the original variable, which is x. So what is u equal to? That is x squared plus 5x raised to 8 all over 8 plus c. So this becomes our answer to this problem. Or even 1 all over 8 times x squared plus 5x raised to 8. So it can be also like this. 1 all over 8 x squared plus 5x raised to 8 plus c. That is still the same thing. Okay? So we are using U-substitution if there is a term in the integrand that can be substituted as a u. And if we get the derivative of that u, okay, the resulting derivative of that u is also present on the integral or the integrand. Okay. So let's try another one. So for example, if we get the 3 minus x raised to 10, okay, dx. Okay. So it may seem like that this is a very complicated question, and again, it's not. Okay? Because if we try to let u, okay, if we try to let u 3 minus x, not including the power of 10, get the du with respect to x on the right side, so we get 0, okay, and then the derivative of negative x, that becomes negative 1. Or simply, that's du all over equals negative dx. Okay? So if we are going to substitute, okay, we know that we only have dx here. And we got here a negative dx because the derivative of negative 1 is negative dx. Or negative, the derivative of minus x is negative 1. So it happens to be negative dx. So if I'm going to multiply this both sides by negative 1, we have negative du equals dx. So the purpose of doing that is that we want as much as possible all inside the integrand to be substituted as u and du, in terms of u and du. So upon doing that, we now have integral of 3 minus x equals to what? We let that as our u. So that would be u raised to 10. And dx is equivalent to what? Okay, and equivalent to negative du here. So you have negative du. Okay, by power rule or by constant rule, we know that, okay, there is a negative 1 here for the du. So I can factor out negative 1 outside of the integral sign and then integrate. So you have negative of u raised to 11 all over 11 plus c. That would be equals to negative u raised to 11 all over 11. Even though we get this as negative, still, that is still a constant. So we might as well proceed with positive c. So again, back substitution. So u equals 3 minus x. So we have negative of 3 minus x raised to 11 all over 11 and then plus c. So this will be our answer for this number 2 problem that we have. Okay, so number 3. It's very useful. I hope you're learning something about this, and I hope you can master U-substitution by this video alone. So 7x plus 9. You know, the most common problems, okay, that the students are scared, okay, is that when they see a radical sign. Okay, so the number 1 thing that we're going to do is to convert that radical sign into exponential. So we have 7x plus 9 raised to 1/2 dx. And if we let u equals 7x plus 9, we know that the derivative of that with respect to x would be 7 dx. Okay, and we need to substitute u here, and we need to substitute dx here with the du also. So I'm going to divide both sides by 7 here. Okay, so this becomes du all over 7 equals dx. I'm doing that to substitute all of the integrand in terms of u. So what happens? So square root of 7 of x plus 9, or 7x plus 9 raised to 1/2 would become what? U raised to 1/2. Okay, we simply substituted this. Okay, and now where is the dx equal? The dx equals to this. So that's why we divide both sides by 7, because we want to obtain dx. Okay, so what happens? We now have, okay, we can factor out 1 all over 7 outside of the integral sign because that's constant rule. So 1 all over 7 integral of u raised to 1/2 du. Okay, and then proceed with the integral. So that's power rule. 1/2 plus 1, that becomes 3/2 all over 3/2 here. Then we have plus c. Okay, so simplify this. You know, we can get the reciprocal of this and then multiply it directly to u. Okay, that's the operation of that. So we have 1 all over 7, get the reciprocal 2/3, and then multiplied by u raised to 3/2. Okay, so that's basic. So numerator by numerator, we have 2 all over 21 u raised to 3/2 plus c. But take note that we have to substitute it back to its original variable, which is x, so that u equals 7x plus 9. So therefore, we have 2 all over 21, 7x plus 9 raised to 3/2 plus c. So that would be our answer for this problem number 3. So it's pretty easy if we convert, okay, into U-substitution, because by doing so, okay, we are able to solve that given problem. Now, not all of the problems U-substitution can be solved by U-substitution. Of course, there are a lot of direct problems, power rule only, no need for U-substitution. But for most of the integrals, okay, given, okay, for us to solve during our integral calculus, you will be employing U-substitution as part of the solution of the integral. So it's very important for us to really master this. Okay, so and for that I have prepared, I think, 10 questions. No, so we have x cubed, going on to number 4, then 1 plus x raised to 4, okay, raised to 1/3. So usually the key in U-substitution is that most of the time, okay, the term that has a high exponent, let's say raised to 7, raised to 6, raised to 10, raised to 100, okay, that whatever that is the term that we're going to let as u, okay, or to let u. So in this case, we have x cubed all over 1 plus x raised to 4 raised to 1/3. So my question is, which of the two, is it x cubed or the 1 plus x raised to 4, can be used as u? Okay, that's right. That's the denominator. We'll see why. If we let u 1 plus x raised to 4 and differentiate it, okay, with respect to x, that would be 4x cubed dx, of which we have an x cubed dx here on the numerator. So if I'm going to rewrite that, that can be also rewritten as x cubed dx, 1 plus x raised to 4 raised to 1/3. But the problem is we only have x cubed dx, but we have 4 here. So I have to find a way to eliminate 4 on this side of the equation so that I can substitute only x cubed dx, because I have only x cubed dx on the integral. So if I'm going to divide this both sides by 4, this becomes du all over 4, and I have x cubed dx, and then we substitute. So we have integral of x cubed dx, that's du all over 4. I simply substituted this by this because of this equation that we have got from our u. And then all over 1 plus x raised to 4 is u, and raised to 1/3. Okay. Constant rule, I can factor out 1/4 because of the du all over 4. I do have du all over u raised to 1/3. Okay, so what will I do with that? I can do what? Okay, I can get this up by negating its exponent. So we have 1/4. So I have 1/4 integral of u raised to negative 1/3 du. So power rule, okay, if I do that, that becomes u raised to 1/3 plus 1, that becomes u raised to 2/3 all over 2/3 plus c. Okay, and then get the reciprocal of 2/3 and proceed to multiplication with the u. Okay, so you also have 1/4 times 2/3, that becomes, this would cancel, this becomes 2. Okay. No, it's actually, I'm sorry. We need to get the reciprocal. Okay. So we need to get the reciprocal. This must be 1/4 and then this must be 3/2. Okay. Because 2/3 is the original and we reciprocate it, that becomes 3/2. So 3 times 1, that's 3. 4 times 2, that's 8. So 3 all over 8. Multiplied by u raised to 2/3 plus c. Okay. And don't forget to back substitute what is x, that is 1 plus x raised to 4. So that becomes 3 all over 8, then 1 plus x raised to 4 plus c. So that is our, okay, original answer for this problem. Okay, I hope you're learning something in our lesson for this. No? It's so easy to do integrals if you know the basic rules, and of course the U-substitution. So for number 5, I have the integral of e raised to 5x plus 2 dx. So we have here an exponential function. So usually, if you're going to recall, we know that the derivative or the integral of e raised to x dx is simply e raised to x plus c. So as much as possible, we want to reduce this into a single variable. So if we also get the e raised to u du, that would be e raised to u plus c also. So I'm going to let u as 5x plus 2. And if I'm going to get the derivative of that, that would be 5 dx. The derivative of 5x is 5. Derivative of plus 2 constant is 0. So that's why we have 5 dx. So dividing both sides by 5, because I only have dx here. I don't want to have a 5 here, so I'm dividing both sides by 5. Du all over 5, and I have dx. So continuing with our integration, I can now substitute e raised to u, which is 5x plus 2. Okay, and then dx is equal to what, or equals what? Du all over 5. So I can now factor out 1/5 outside of the integral sign. And there you go, e raised to u du. And that is a very easy question. That would be 1/5 e raised to u plus c. Okay, but take note, we have to go back to the original variable, which is x. So u equals e raised to 5x plus 2 plus c. So this will be our answer for this given problem. Right? So another one. Let's finish this. So I have number 6. The integral of 4 cosine of 3x dx. Okay? So we can recall that the integral of sine, or integral of cosine of x dx equals sine of x plus c. Okay? So, but the problem here is we have 3x, not simply x. So you cannot just simply do the integral of, let's say, integral of cosine of 3x dx as sine of 3x plus c. That's now not how it works. The given in the formula, if you're going to look for the integration of trigonometric function, is this: the cosine of x dx equals sine of x plus c. And that is also the same if we have cosine of u du, that would be sine of u plus c. So as much as possible, we want to let u as the 3x, the one that is inside the trigonometric function. If I let u equals 3x, the derivative of that would be 3 dx. So I'm going to rearrange this. We have 4, so we can factor out 4 outside of the integral, and then we have cosine of 3x, and then we have dx. So I only have dx here, so I'm going to isolate dx here on the right side by dividing both sides by 3. So you have du all over 3, and you have dx. So we're all good. So we have 4 integral of cosine of 3x, which is u. Okay, and dx equals to what? du all over 3. So factor out 1/3. So I have 4 times 1/3, constant rule, cosine of u, and then du. Okay, whenever we have a constant inside the integral, we can factor it out, especially if it is multiplied or divided. So you have 4/3 cosine of u. What is cosine of u? That is simply sine of u, okay, plus c. And going back to the original variable, since this is in u, what is u? That is 3x. So 4/3 of sine of 3x plus c. So this will be our answer for this problem number 6. Okay, so what we did, again, cosine of 3x, integral of cosine 3x of dx is not equivalent to just sine of 3x plus c. Okay, so because the formula for integration is this, the x must have a constant value or coefficient of only 1 for us to use these formulas. So we have reduced it by converting that 3x into U-substitution. How about 7? For number 7, if we get the integral of sine of ln of x all over x dx. Okay, so this is a little bit tricky in a sense that what do I get? What do I let u? Okay, so remember that this ln of x is inside the sine. Okay, so 99% of the time, 90% of the time, okay, whatever is inside the trigonometric function, that becomes the ln, or that becomes the that becomes the u. So if we let u ln of x, then get the derivative of ln of x, that's 1 of x dx, 1 over x dx, or dx all over x, of which, if we are going to rearrange the original given, it could look like this: sine of the ln of x, okay, multiplied by dx all over x. That is still the same, okay, because this is multiplied or divided by 1 all over x. So that's dx all over x. So we have seen dx all over x here. So we can now substitute sine of, okay, our ln of x is now u. So that's u. Dx all over x equals what? Du. So that is simply the integral of sine of u du. And that is negative cosine of u plus c. Okay? Going back to the original derivative or original variable, we have negative cosine of the ln of x plus c. Okay? Back substitution. Okay, remember to always go back to its original variable whenever you employ U-substitution, because unless otherwise your answer will be wrong if you don't substitute back to its original variable. Alright, so for number 8, let's try another one. For number 8, so you have 3x plus 6 all over x squared plus 4x, okay, minus 3 dx. So it's obvious. If we get the derivative of the denominator, we'll be having 2x, right? So let us get let u as x squared plus 4x minus 3. Get the derivative of that u, power rule of differentiation. So you have 2x plus 4 dx. Oh, sir, we don't have 2x plus 4 dx in the integrand. This is not 2x plus 4. Yeah, that may be your observation at first. But if you take a look at closely of 3x plus 6, if we try to manipulate it, okay, in such a way that I'm going to factor out 3 factor out 3, I have x plus 2 dx all over x squared plus 4x minus 3. And in the same way, if I'm going to factor out 2 here, okay, in our du, factor out 2, I have x plus 2 dx, which happens to be this one. Okay? So I have here x plus 2 dx, which is present on the integral. So I can factor out 3. I can divide this by 2. So what happens? I have du all over 2. I have x plus 2 dx on the other side. Okay? I can now substitute x plus 2 dx. Where is that equal? Du all over 2. So that becomes du all over 2 all over u, which is x squared plus 4x minus 3. So that's our solution. I'm going to write it neatly here. 3 all over 2. Factor out 1/2, that becomes 3/2. Integral of du all over u. Okay? If we integrate du all over u, we know that that would be 3/2 ln of absolute value of u plus c. Du all over u is the absolute value. So going back to its original variable, what is the u equal to? We have x squared plus 4x minus 3. We have x squared plus 4x minus 3. So that will be our answer for this given problem. That's the U-substitution. That's how it works. Right? That's how it works. For number 9, we have 3 all over x ln of x dx. Okay? This may seem to be a little bit tricky, but it's the same thing. Usually, whatever is obvious here is that I can factor out 3 outside of the integral sign, and I have dx all over x ln of x. So how do I integrate this? So we have seen a lot of integrals a while ago that involves ln, and let's give ln of x, okay, a worth of a try if we let that as our u. So ln of x. So that becomes du equals ln of x, the derivative is 1 all over x dx, or simply dx all over x. So if we're going to rearrange this integral, that becomes 3 integral of dx all over x multiplied by 1 all over ln of x. Coincidence? No. Okay, so we can now substitute dx all over x. What is dx all over x? That's du. Simply du. And what's ln of x? That is u. So that is 1 all over ln, or 1 all over u. Okay, so if you do that, we are what? We have du all over u. Okay, so it's very easy. That will become 3 ln of the absolute value of u plus c. Going back to the value of u, what is u? Ln of x. So you have 3 ln of the absolute value of the ln of x plus c. Okay, so this would be our final answer for this. So you see, employing U-substitution is really great. Okay, so how do you know that if a problem has a U-substitution? My only answer to that is through experience of solving integrals. First, you try first, no? Here's my tip. If you see an integral, and if you can integrate them directly into power rule, okay, ln, log, okay, or if there is a direct formula that can integrate that integral, then you must use it. But if there is none, okay, your second option is U-substitution. Okay, so most of the time you can solve it by U-substitution. If not, U-substitution becomes a part of your solution for different techniques of integral. So number 10, And by the way, the last number for this problem or this discussion, so we have x multiplied by 3 raised to x squared plus 1 dx. It's very obvious that if I have an exponent like that, x squared plus 1, might as well give it a try. X squared plus 1, then my du would be 2x dx. Oops, if I'm going to rewrite this, that would be 3 raised to x squared plus 1 multiplied by x dx. So I'm going to divide this both sides by 1 or 2. So we have 2 du all over 2. We have x dx. So I can substitute. Okay, I can substitute. So we have 3 raised to u. X squared plus 1 becomes u. And x dx is du all over 2. Factoring out the constant 1/2. Okay, if you haven't watched my video about the constant rule or the basic rules, you must definitely watch it. So you have 3 raised to u, and then we have the u. So this is a simple formula of getting the integral of this. So that becomes 1/2. Looking at the formula, of course, no? So we do have 3 raised to u ln of 3. Okay, so plus c. So we have a formula, a basic formula in integrals, that if we have a raised to u, where a is any number, constant number, du, so the answer to that would be a raised to u all over ln of a. Okay, which happens here. So and so, if we're going to go back to its original form or original variable, okay, that would be 1/2, okay, multiplied by 3 raised to u, which is x squared plus 1 all over ln of 3, okay, plus c. Or in other words, that's 3 raised to x squared plus 1 all over 2 ln of 3 plus c. So that will be our answer. It's still the same as this one. Okay, so these are the same. And that's it. I hope you learned something from this video. If you're new to my channel, please don't forget to subscribe for more integral calculus video. I've been doing a lot of videos about integral calculus, so make sure to subscribe and to follow my playlist on that, so that you will be able to pass your integral calculus subject if you really want to pass it. Okay, so I hope you learned something. Thank you so much, and don't forget to subscribe. Again, this is Engineer Abat. See you on the next video.